All right, we've got three examples that we'll use the comparison test on. We've got example 1, the series whose terms are 1 over n cubed plus 3n plus 1. The second series has terms 1 over 2n plus 1. And the third series has terms 1 over natural log n. And in that case here, n starts at 2. It can't start at 1 because natural log of 1 is 0. So let's dig into the first example, the series whose terms are 1 over n cubed plus 3n plus 1. Notice that this is a polynomial, and here it's a polynomial n, and I've got a power of 3. So I know that the p series, 1 over n cubed, converges, and I know that 1 over n cubed is going to be larger than 1 over n cubed plus 3n plus 1. Why? Because when I add non-negative terms, 3n plus 1, that'll make the denominator larger than if I just had 1 over n cubed. And so that larger denominator will make this value here for each of those terms in the series, it'll make it smaller. So I know that this term, for all the terms, are in fact smaller than the terms of the p series, where I have 1 over n cubed being the terms of the p series. So let's go ahead and formally write that up. Okay. So here I'm going to call our series in question for the first example, the series of terms 1 over n cubed plus 3n plus 1, and each of the terms I'll just call a sub n. And I'll take b sub n to be 1 over n cubed, because I know that 1 over n cubed is bigger than or equal to 1 over n cubed plus 3n plus 1 for all n bigger than or equal to 1. So there I have my relationship. These are the a sub n's less than or equal to b sub n's for all n bigger than or equal to 1. Here I've stated it, just like I have in the theorem for the comparison test. And then since we know the series whose terms are b sub n, meaning 1 over n cubed, converges by the p series, where n equals 2, which is bigger than 1, then because that converges, and all the a sub n's are less than or equal to b sub n's, then by the comparison test, the series whose terms are a sub n converges. So this example here converges by the comparison test, where we compare it to 1 over n cubed. Let's look at example 2. So for example 2, I have 1 over 2 to the n plus 1 as my terms in the series. And this should kind of remind you of the geometric series where I had 1 over maybe 3 to the n power, or 2/3 to the n power, or 3/8 to the n power. I had a ratio r to the n power. As long as the absolute value of r was less than 1, then that geometric series converged. So here I'm thinking, what about if I look at 1/2 to the n power? Okay, so for all the terms of just 1 over 2 to the n, it's going to be 1/2 to the n power. All of those terms will be in fact less than 1 over 2 to the n plus 1, because this denominator is bigger than just 1 over 2 to the n. So a bigger denominator means it's going to be smaller. So these terms here, 1 over 2 to the n plus 1, are in fact smaller than 1 over 2 to the n. So I'm going to take my b to the n's to just be 1 over 2 to the n, and I know that those terms, that series will converge by the geometric series for r, absolute value of r less than 1, and therefore by the comparison test, my a sub n's, which are 1 over 2 to the n plus 1, will also converge. So let's go ahead and formally write that up. All right, so here I've got my series in question. I'm going to call that the sum of the a sub n's, where the a sub n's are 1 over 2n plus 1. I'm going to take the b sub n's to just be 1 over 2 to the n. And note that our a sub n's, 1 over 2 to the n plus 1, are in fact less than or equal to 1 over 2 to the n, and that's the b to the n's. So then I have the inequality, a sub n's are less than or equal to b sub n's, all which are bigger than or equal to 0. So now my b sub n's, which I recognize, that's a geometric series, converges in fact to 1/2 over 1 minus 1/2. Here the 1/2 here is a. Here the 1/2 down here is our r. Our r is 1/2, which is less than 1, and a is 1/2. So that converges to the number 1. Therefore, By the comparison test, our series whose terms are a sub n also converges. Let's look at example 3 next. Here in example 3, I have the series of terms 1 over natural log n. Now, natural log n is a log function whose base is e, and that grows very slowly. In fact, natural log n is less than or equal to n for all n, in fact, bigger than or equal to 1. So here, we could pick the harmonic series whose terms are 1 over n, and 1 over n, since n is in fact bigger than natural log n for n bigger than or equal to 1, 1 over n will be smaller than these terms of 1 over natural log n. But we know that 1 over n as terms in the series will diverge. And so since these are larger than 1 over n in their respective series, it also diverges. So let's go ahead and write that up formally for example 3. All right, so here I've got my a sub n's as 1 over natural log n. And I'm going to take b sub n's as 1 over n. Again, those are the terms in the harmonic series. And I note that 1 over natural log n is less than or equal to 1 over n for all n bigger than or equal to 1. So what that means is the b sub n terms are in fact less than or equal to the a sub n terms. But I know that the b sub n terms in the series make up the harmonic series, which diverges. Then by the comparison test, the series of a sub n's also diverges. And let me correct that. All right, let's go on to the limit comparison test, which is slightly different than the comparison test.